Well, just wait till you get to general relativity, where it's all in these goddamn indices. You know, you write down some symbol and then there's I, J, colon, or semicolon, or a comma in the indices, which mean things like taking the derivatives, the gradient, and all kinds of things like that. Extremely compact notation and very hard to get used to.
Yeah. Okay, so we're given this point transformation Q in terms of the S's. We assume we can invert this so we can get the S's as a function of the Q's in time. So I'm just going to work something out here for use in just a minute. I'd like to find ds I dt, this one right here. So that's just going to be sum over j here of partial si partial qj dot plus partial si with respect to t. Everyone agree?
Mm.
And this is si dot.
Yeah.
Okay, so next thing we can do here is take partial si dot with respect to qj. And so we can see, I'm not going to show the Kronecker delta, it's been done just a moment ago. You get rid of this and you get rid of all terms except one in this series.
Yeah.
So then you just get partial si with respect to q. There we go. Dots just keep disappearing everywhere. Okay. And similarly, if we show there's no q dependence here, so we can say partial si dot with respect to qj is just 0. Okay, so these, hang on to these for just a moment.
Pretty sure that term on the left that you squared is an identity in the book. Or not identity, it's given. Yeah, I think he shows that.
Then maybe this is how to prove it. That's equation 1.65.
Yeah, okay.
I believe.
So we didn't do all that work.
Yeah. Okay, so now we have to Euler Lagrange equation.
It's one of those that looks like it's a lazy cheat. I'll just slip a dt in on the top and bottom.
With respect to ui dot.
It's kind of like Mady tells the story of this astrophysics guy who made second order differential equations easier by taking the square root of both sides.
Did his satellite crash?
So we do this.
Real work.
Do a little chain rule. Oh, and I should say my L here is now a function of the S's. Sj, Sj dot in time. Okay, so take partial L, partial Sj dot. Okay, we've just done chain rule. Dot. Minus partial L, partial qj. Qi. Rise. Okay, well, this thing here, we just figured this out. We can get rid of the dots. So this turns into, start back over here again. D by dt, partial L is back to S j dot. Now it's partial Sj over partial Qi. Okay, I'm going to copy this down for a second. Yeah. Okay, now we're going to do product rule on the total time derivative here.
Yeah.
So just d by dt of partial L with respect to Sj dot times partial Sj with respect to Qi plus dot times time derivative of partial Sj respect to Qi. Copy the last part down here. Okay. Now, so one more step from here. Do the chain rule here again. Partial L with respect to Sj. Partial Sj with respect to Qi. So now we got partial Sj, partial Qi. Same thing over here, so let's factor this. So now we get d by dt partial L with respect to Sj dot minus partial L with respect to Sj, whole thing times partial Sj with respect to Qi, plus, I can take this down here, partial L with respect to Sj dot. Now, this just evaluates to partial Sj dot with respect to Qi. And then our last thing here says that this goes to 0. So what we have, this whole thing's got to be 0. And this partial here, we can't say in general is 0. And so that we can conclude that this whole expression in parentheses has to be identically 0, which gives us our Euler-Aron equation in terms of the S's instead of Q's.
Good. Yeah.
Yeah, quick question, just because this is like what I still don't really believe about mine, is when you say like partial S dot is partial Q is equal to 0, yeah, right there.
Yeah.
Why can we say that when there are partial like Q's in the, like still there, like potentially partial Q, partial T could be a function of Q, right? Is
I think
that,
I followed you mostly. You believe in this equation here?
I believe in that. But like, I don't know, this is what I got really hung up on. I was imagining some like, what, is that an S or, that's an S, like the second part, that's partial S, partial T?
This is partial S.
Right, no, the part that's partial T over on the right.
Up here, right?
Yeah, that.
Yeah, partial SI, partial T.
Yeah, that's, I don't, it seemed like you could potentially have that be some sort of function of Q.
Okay.
I wasn't like,
Well, again, partial derivatives here are
Yeah.
only non-zero when there's an
when
explicit
there's an explicit Q.
If
Okay.
you have some
That, yeah,
You know,
that was holding me up.
partial with respect to, z of some type of z here, that's 0.
Okay.
So only if you actually have a,
An
z,
actual Z.
that will, it's the only case. The total time derivative is a different story.
Right. Okay, I guess I didn't really.
Yeah, what-
That's what I was talking about the last night, right?
No,
Right, and
it's
is
this
why
condition, the second condition.
Yes.
Much of this stuff is
What to
very
justify.
unintuitive. You just-
Yeah, it's hard
It's
for
hard
me
for
to
me to
imagine.
imagine.
Because otherwise you
about
have that
everything.
term non-vanishing.
The chain rule and the partials.
And that, yeah, that seems to be like crazy.
By the way, I was looking up, when I looked up the Nielsen form and alternatives, thank you,
That wouldn't set people to zero.
the
That
Nielsen
justifies it.
form, and found some of these others. One of them I found was a reference to Chaplygin's form. Chaplygin was a Russian physicist from back around 1900. And he's best known these days for Chaplygin gas, which is a theoretical gas which has a particular equation of state, which if you plug in for cosmology, you can maybe get dark matter and dark energy both out of the Chaplygin gas. And so it's something people have been working on for a long time, but they can't really quite make it work. But it's one of those weird things in the history of physics. At any rate, I think there's something interesting there to look up about all these different forms. There's Eric lurking out here. Put in your contributions. And So, remember, we're gonna do, for the final, we're gonna do presentations. And I was thinking a topic for a presentation, which might be fun, would be to look up some of these varieties of
Lagrangians?
Lagrange's equations, and do a little report on them.
Oh, yeah.
Some of them that are out there, it looks like